We'll continue the analysis of Doherty power amplifier. In the last lecture, uh, we analyzed the Doherty power amplifier for lower drive. That means when input is less than certain chosen threshold. For that case, we found out what should be the characteristic impedance of the transmission line and what should be the load, so that maximum swing of VDD is achieved at the drain of main power amplifier. So here we have Doherty power amplifier. And the input is of this form, where beta varies between 0 and 1. So we saw that for low drive, that means when beta is less than threshold, certain chosen threshold, for this case, Z0 should be equal to RLB, where RLB is the load corresponding to class B of operation when the drained voltage attains the maximum swing of VDD. And this RLB is defined in this way. So IP is the maximum swing of the drain current when the voltage has the maximum swing. So this is going to be the location of the drain voltage. And we have been calling this as VDM. Both the power amplifiers, main and auxiliary, are going to be operated in class B mode of operation. So this was the requirement for characteristic impedance, and the load for this Doherty power amplifier should be beta T into RLB, such that for beta is equal to BT, the threshold value, the drain voltage becomes equal to VDD. And when this happens, the efficiency becomes equal to the maximum, equal to that of the class B case. So main power amplifier attains the maximum swing and maximum efficiency for this input. Now our objective in this lecture are going to be that first we will try to find out what should be the current provided by this second power amplifier, the auxiliary power amplifier, such that even for the higher drive, the voltage at the drain of the main remains VDD. So what we have already done is this part. So this is maximum efficiency for class B. So we, by choosing these values of the impedances, we have been able to achieve this maximum voltage swing. Sorry, that was the efficiency. So what now we want, that even for the remaining part, the voltage should remain equal to VDD. So this is required. So for this to happen, what should be I2, the current provided by the auxiliary power amplifier. So this is what we will be first trying to find. And then once we find out I2, we will try to show that for the upper drive, when the complete circuit is actually going to be like this, the load continues to get a voltage which is proportional to input. That means voltage is dependent upon beta. So this is the second objective. And finally, we will try to find out the efficiency, overall efficiency, which of course will be divided into two regions, one for the lower drive and other for the upper drive. That means when beta is greater than beta t but less than 1. That means for this region. So here we have lower input or drive region, and this is higher or upper drive region or input region. Okay. So we are now going to find out I2 or the higher drive region. Such that VDM equal to VDD for entire upper drive region. So this is the objective. Now there are certain equations that we will be using, and those are that for lambda by 4 line, we have this relation, and the same relation can be rewritten for the equivalent circuit of that. We will shortly write it. So this comes from the first equation, and then another equation that will be useful is this one. So we have already used this one, say equation 1a, 1b, and 1c. So the equivalent circuit of the Doherty power amplifier for the upper drive for the higher input or drive is going to be like this. So main power amplifier is going to be represented by this current source, which we will be calling as I1. And then now we have lambda by 4 line. And then we have load. And load is also being fed by the auxiliary power amplifier, which will be designated by current source I2. And this is going to be the location of the drain of the first MOS. So this node will correspond to VDM voltage, and of course it will be experiencing current equal to I1. And looking towards the load, we will have impedance which we will call Zin. And on the other side, we will have a current which we will be calling as I1L going to load, and this is of course I2. And the load will be experiencing a current equal to IL. And this voltage we will be calling as the output voltage in which we are interested. So what we have already found out from the analysis for the lower drive is that the Z0 should be equal to RLB, and load should be equal to beta T into RLB, and I1 is the fundamental of the uh, half wave current. So this is half wave because this is in class B. So fundamental is going to be beta into, so this is the fundamental for the total current produced by the main power amplifier. So what we have shown here is only the fundamental, not the complete drain current of the main power amplifier. And of course, we will be using these equations that we have shown here. So, so now we will proceed to find out what should be I2. And also, since the RL experiences current from both main and auxiliary power amplifier, so it will appear as a different load, and we will be calling as Z1L. So this is the load that will appear to I1 and the lambda by 4 line combined. And this load is going to be RL into 1 plus I2 by I1 L. So the current, second current entering into load, this current divided by the first current. So this ratio will play the important role. Okay. So our objective is to find I2 such that this drain voltage is always equal to VDD for the upper drive region. So we start with this voltage VDM itself. So this can be written as this VDM voltage is going to be equal to the impedance looking towards this side, which is Z in, and divided by this current I1. So this is Z in into I1. So now what is this VDM or this Z in? Now we can substitute this Z in using the relation for lambda by 4 line. So this will become Z naught squared by the load at the other end of the lambda by 4 line, and the load at the other end is Z1L. This is the effective load, although the physical load is RL. So we will have to take this effective load perceived by the transmission line. So this becomes Z1L into I1. Now we can rewrite this equation as VDM into Z1L equal to Z01 square into I1. So this becomes VDM, and Z1L we just now wrote is RL into 1 plus I2 by I1L, and this is Z0 square I1. So now here we can see that I2 has appeared in the equation, but now we want only I2. We want to get rid of I1L. So we will try to find how to eliminate I1L. So for that, we will take the help of the equation number 1C. So using this, we will try to get rid of I1L. So from that equation, we see that VDM I1 is equal to minus VO I1L. And from 1B, we have VDM by I1 into VL by I1L is equal to Z naught square. So we can multiply these two equations. So this equation and this. So that will give rise to VDM square is equal to minus Z naught square I1L square. So this is VDM is equal to plus minus J Z naught I1L. So now we can go here and we will try to eliminate I1L. So this is equation 2 and 3. So eliminating YL, what we get is VDM into RL into 1 plus I2 into plus minus J Z naught divided by VDM equal to Z naught square I1. So we can now rearrange them. We will get VDM RL plus minus J Z naught RL I2 is equal to I1 Z naught square. So what we want is I2, so we'll keep I2 on one side. So from here, we can find out I plus minus J I2. If we do this manipulation, it will be Z naught divided by RL I1 minus VDM by Z naught. So here we have found out I2, but it is in terms of I1 and Z naught RL. So we now need to substitute each of these, and in fact VDM also, in terms of the known quantities. So what we do is we have already found out what should be Z naught, and Z naught was equal to RLB, and RL is equal to beta T RLB. I1 is beta into IP by 2 because this is the fundamental of the drain current of the main power amplifier, and this is RLB VDM. So what we want this VDM to be always equal to VDD. So this is desired for this parameter. So we can now do the manipulation and write the final value as beta by beta T minus 1 into IP by 2. And we will have to eliminate this whole factor or rewrite in terms of IP. Recall that RLB was defined as the load for the class B when the swing is maximum, and it turns out to be of this form. So using this, we eliminate this and write in terms of IP, and then this is what we get finally. So I2 then can be written as minus plus j to beta minus beta t by beta t into IP by 2. So this is the fundamental of the current produced by the auxiliary amplifier. Of course, for the higher drive region. And this APA is also going to be in class B mode. So this information will be required later on so that we can extract the DC current drawn by the auxiliary power amplifier, which will be required when we try to find out the efficiency. So without assuming this in one specific mode of operation, we will not be able to find efficiency. So here we see that we have this factor. So this amounts to having a phase. So I2 can be written in this form, beta minus beta t divided by beta t into IP by 2 e raised power minus plus j pi by 2. So here we see that we have a factor which acquires a phase of 90 degree. So that is why if you see the complete architecture, we have this additional lambda by 4 line at the input side of the auxiliary power amplifier. So this line will basically introduce this 90-degree phase shift that is required here. So that is why for the auxiliary power amplifier, it is used in this form, lambda by 4 line. So whatever is the voltage or current here, and at this side, we will have VI e raised to minus j pi by 2. So this additional phase shift is due to lambda by 4 line, this line. Okay. So we have found out what should be the current provided by the auxiliary power amplifier, so that for the higher drive region also, the main power amplifier drain location, this location is always fixed at VDD. That means this is always operating at the high power efficiency. Now, this is fine, but what we want is that my load should continue to get a voltage which should be proportional to input. That means which should depend linearly on beta. So this output should be linearly directly proportional to beta. This is the final objective. So if this arrangement or this circuit is not able to meet this, then it will be of no use. So now we will try to show that whatever value of Z0, RL that we calculated and I2 that we have calculated, that will indeed ensure this requirement. So the second objective now is to show that for the load VO is proportional to beta. That means proportional to VI for the upper drive region as well. For this case also. So now we start with the equation 1C and 1A. So actually we multiply these two equations. So we get VDM I1 equal to minus VO IL. So this is the equation 1C. Now we multiply it with 1A. or different form of 1A, not exactly, or rather 1B in fact, Z0 square. So this will lead to VDM VO divided by I1 I1L. So this gets simplified to I1 square Z0 square is equal to minus VL square, or so this is not VL, rather this is VO. So VO square or VO is plus minus J Z0 I1. But we know that Z0 is RLB, and we know that I1, which is the fundamental of half-wave rectifier, is beta IP by 2. So this becomes plus minus J beta RLB IP by 2. But this factor is equal to VDD. So here we see that output is indeed proportional to beta. That means it is linearly varying with respect to the input, which is required. So here we can also try to find out what will be Z1L, the parameter or the impedance that the main power amplifier along with the lambda by 4 line perceives. So we have already seen Z1L is equal to RL into 1 plus I2 by I1L. Now, this equation we will be requiring later on, so we can call it 5. Yes, 5A. And I2 we have already derived is beta minus beta t by beta t into IP by 2 into e raised power minus plus j pi by 2. So now, and we can also find out what is VDM, which is plus minus j Z0 I1L, and Z0 is RLB. And for this entire upper drive, because we are finding out this for the upper drive region. So for upper drive region, this VDM is going to be VDD. So this is plus minus J RLB I1L. And this plus minus J can be written like this. So this is, say, let us say equation number 7. So we can do 6 into 7. So that will give us I2 VDD square to beta minus beta t by beta t IP by 2 raised to minus plus j pi by 2 into RLB I1L e raised power plus minus j pi by 2. So here these two exponential factors, they will cancel out, and what we will have is I2. We can take I1L this side, left side. So this becomes, right side becomes beta minus beta t by beta t into IP by 2 RLB, and this is equal to VDD. So what we will have is I2 by I1L is equal to beta minus beta t by beta t. Right. So this becomes 1 plus I2 by I1L is equal to beta by beta t. So we have taken out 1 from right side to the left side. Now we can multiply both sides by RL. So this left side becomes Z1L, and this is equal to beta by beta T RL. But RL we know that is beta T into RLB. So the load perceived by the main power amplifier and lambda by 4 line together is beta RLB. So here we see that load modulation is taking place for the upper drive region because of the auxiliary power amplifier, and it is varying linearly with the input. So now the third and final objective is going to be finding out the efficiency. So when we try to find out efficiency, of course, this will get divided into two regions, because the complete circuit assumes two different circuits for different value of the input. So there is a one input range which is called lower drive region, and then we have upper drive region. So we will have two efficiencies, of course, for the lower drive region and efficiency for the higher drive region. So we will have to find out each of these two one by one. So let us first try to find out the lower drive region efficiency. So this is also, of course, going to be the power delivered to the load divided by DC power drawn by the main power amplifier. So this PDC is the DC power drawn by MPA. Keep in mind that APA is off for this case. So there is no power dissipation in the auxiliary power amplifier, and the load power is also only due to the MPA. So for this case, the circuit is going to be like this. So this is our main power amplifier, which is then connected to lambda by 4 line, and then ultimately to load. So to find out efficiency for this case, the auxiliary power amplifier is open. So we need to find out what is IDC that is being drawn from here, and what is the current to the load. So keep in mind that this is going to be the current to the load. So this is what we have to find out. And this voltage is of course going to be VDD DC voltage. So this is always going to be VDD DC. So therefore the DC power is going to be VDD into IDC. And this drain current is half wave rectified like this with peak IP, or rather beta IP, because this will vary with the input. So the IDC part is going to be beta IP, the peak of the half wave, divided by pi. So therefore PDC, and this is for the main, and during the lower input case is going to be VDD into beta IP by pi, so which becomes beta VDD IP by pi. So here we see that as the input varies, the DC power consumed by the main MOS is also varying. So now we have to find out PL. So PL is going to be decided by this VO. So we have used this VO for all the cases for lower and upper. So we will always write the power delivered to the load in terms of this voltage. But keep in mind that for the lower drive, although I1L is the current that will be ultimately flowing through the load, but for higher drive region, I2 will also come into picture. But during higher drive region also, the output voltage is going to be V only. So it will be better or safer to always define the power to the load in terms of this voltage. So the power to the load is going to be VO square by 2RL. And what is VO? VO we have in fact derived here, equation 5. So this VO is beta VDD square by 2RL. But here, in fact, it can also be written in terms of IP, because VO we have also found out to be equal to plus minus J Z naught I1. So we want to write in terms of IP also, so that this IP appearing here can be then cancelled out. So it can be written either in terms of VDD or I1, and ultimately in terms of IP also. So these are the two ways in which it can be written. So we will be using this one. So therefore efficiency for lower drive, which is PL by PDC, becomes Z naught square beta square IP square coming from here divided by 2 RL. In fact, it will become 8 RL, and then beta VDD IP by pi. So this will simplify to pi by 4. Now we can write Z0 and RL in terms of RLB. So we know that this factor is going to be equal to 1. So load drive efficiency becomes pi by 4 beta by beta t. So this is for load drive case. So here we can make a plot of this. So this is beta, that means input, and let us say this is the threshold. And here you can see that this lower drive efficiency for beta is equal to beta t is equal to pi by 4. So it attains the maximum value of pi by 4 for this threshold, and it varies linearly like this. But if we superpose on this the plot for class B, then this is what we will get. So this is for class B. So here we see that the Doherty power amplifier, for every value of the lower input region, offers more efficiency compared with the class B case. And it attains the maximum efficiency for a smaller value of input. But for usual class B, one has to go for the maximum full range of the input to achieve efficiency of pi by 4. So for lower region also, it is already offering a better opportunity. And typically, this beta t is taken to be 1 by 2. But one is free to choose whatever value they want. So we will later on point out why it is 1 by 2, why it is not 1 by 4. For that case, this graph would have been like this. So if you take beta t smaller and smaller, you will attain the maximum efficiency sooner, and there will be more gap between the actual class B case and the Doherty power amplifier. But this is not desirable. We will see that why it is not desirable. Now let us try to find out efficiency for higher drive region. For this region. So in this case, the auxiliary power amplifier, it will also come into existence. So now both are active. So that means both consume or draw DC power. So this one as well as this both will now draw the DC power. So they are connected to VDD. This one is also connected to VDD. So both will be drawing DC current. Here, like this. So in this case, the main definition remains same, but now this PDC is going to have two components: DC power drawn by the main and the DC power drawn by the auxiliary power amplifier. So this PDC formula will remain same because the drain will always be at VDD and it will continue to draw a certain DC current, and this DC current is going to be beta IP by pi. So for main power amplifier, the DC power drawn is given by this equation. Now for auxiliary power amplifier, we will have to see that what is the DC power drawn by this. So this auxiliary power amplifier is also class B. So circuit for auxiliary is also going to be like this. So it will be drawing drain current, let us say I2, right? And we have already found out the fundamental of this. I2. So this thing we have already found out. And using this, we will try to find what is the DC current drawn by auxiliary power amplifier. So here, what is I2 that we found? I2 is equal to beta minus beta T by beta T into IP by 2 e raised power minus plus j pi by 2, right? So this is the fundamental, and keep in mind that fundamental of half wave is equal to the peak divided by 2. So this is the fundamental. That means the peak is beta minus beta T by beta T into IP e raised power minus plus j pi by 2. So this is the peak, right? So this peak is for the second case, auxiliary power amplifier case. So from here, we can now see that, or the magnitude is in fact going to be only this much. This is the phase part. So if the peak is known, then we know that DC of this waveform is peak by pi. So this is going to be the DC. So from the fundamental of the auxiliary, we extracted the peak. Once peak is known, we can find out the DC part using this formula. So therefore, the IDC of the auxiliary is beta minus beta T by beta T. Of course, 1 by pi will be here. IP, like this. And DC has no fades, so this is going to be the DC part of the auxiliary power amplifier. So we now know the DC part, DC current from the auxiliary power amplifier. Therefore, and for DC, auxiliary also, the drain is always going to be at VDD DC voltage because it is connected to VDD through RFC. So therefore, PDC auxiliary is going to be VDD into IDC auxiliary. So this becomes VDD by pi beta minus beta t by beta t into IP. Right, so this can be rearranged. This. So therefore, the total DC power drawn PDC main plus PDC auxiliary, and this will become beta plus beta minus beta t by beta t into VDD IP by pi, and now we have to find out the load power. So load power, as I pointed out, we will always define in terms of the output voltage like this. Because now for the higher drive region, it will experience current from both the amplifiers. So we have to see that what will be this expression. And we know that we have already seen that this output is proportional to plus minus J beta VDD. So therefore, PL is equal to beta square VDD square divided by 2RL. And we know that RL is actually RLB into beta T. So denominator we replace in terms of RLB, and numerator it remains as it is. So this is the load power. So we can call this as say equation, let's say 8. This is equation number 9. So therefore, for higher drive region, efficiency now can be calculated. So this becomes equation 9 divided by equation 8. So if you so if you carry out this complete analysis, the final expression will be pi by 4 into beta square divided by beta into 1 plus beta t minus beta t here. So now we have efficiency relation for both the regions. So this is for this region. So therefore, the efficiency of Doherty power amplifier can be written as pi by 4 beta by beta t for lower drive region, and pi by 4 beta square by beta into 1 plus beta t minus beta t. This is for higher drive region. So as was pointed out, typically we take beta t is equal to 1 by 2, the threshold. So for this case, the efficiency will be pi by 2 beta and pi by 2 beta square by 3 beta minus 1. So now if we plot this function, so this varies linearly for the lower drive region. And as was pointed out, a usual class B will have this relation. Now what will happen for this case, beta is equal to 1 by 2, is that in the higher drive region, we will get this kind of response. So this is when we take beta is equal to 1 by 2. So one will be tempted to say that why not to take say beta as 1 by 4, even smaller value. So what will happen for 1 by 4 is we will of course for the lower drive region have higher efficiency, but unfortunately for higher drive region, the response will be like this. So here we see that for higher drive region, although the efficiency is higher compared with the usual class B, but then it does achieve a lower value. And how low it goes actually, unfortunately, depends upon beta, this threshold. So if you take beta smaller and smaller, this value is going to be smaller and smaller. So on the whole, this will degrade the overall efficiency. That is why typically we do not take beta t to be very small, and beta t is equal to 1 by 2 is a typical value. So here, when we take beta t is equal to 1 by 2, we are basically saying that input is half of the maximum, right? So if we calculate it in terms of dB, so this half will corresponds to 20 log 1 by 2, which will be minus 6 dB. So this x-axis, which we have designated in terms of beta up till now, is also designated in terms of, say, input voltage or input power. And in dB scale, this 1 becomes 0, and this beta t is equal to 1 by 2. This point becomes minus 6 dB, so on and so forth. So we say that for this case, for beta t is equal to 1 by 2, the input power is reduced by 6 dB, or input power is backed off by 6 dB. So beta t is equal to 1 by 2 is also called minus 6 dB backed off power. So this backed off, you can see that is synonym for reduced. So we can choose a threshold for minus 6 dB backed off case. So minus 6 dB compared with the maximum value, which is 0. So typically, this Doherty power amplifier design will be described or talked about in terms of this backed off parameter, which is nothing but the log version of the beta t, 20 log of this. And it equivalently represents how much less power we have to give to achieve this threshold point, this point or this point.